So far, we discussed the number system, right? Numbers system, right? And we had the most famous one, which is hex, octal, and binary. We learn also from there BCD, right? And also we covered how to convert from one to the others in integer and floating, which is a real number. Real number like, 1.3, 1.4. Let's go real number. Okay. Anyway, then you talked about the parity bit. Parity. And also we talked about, the two's complement, one's complement, and r's complement, and r minus one's complement. We talked also about the what else we talked about? We think that's basically what we have, right? And we talked about XS3, right? And we talked about yeah, I mean, that's pretty much what we have for this chapter. Then we move to the Boolean algebra, right? That was chapter 2, if you guys remember. When I say chapter 1 and chapter 2, we are talking about the same book, right? With the Morris, right? The Morris version that I gave it to you before on the Slack. Do you remember? Hello.
Yes.
Everybody have a copy of this, right?
Yes.
Okay, so when we talk about Boolean, we talked about, the postulates for optimizations. And the most famous, it was the what's called De Morgan theorem, with x ORed with 0, x ORed with 1, x AND with 1, x AND with 0, and so on. Then we have several examples on optimizing using postulates.
What does that say? De Morgan, De what?
De Morgan theorem.
Theorem, okay.
Okay. Then we move into what? The definition of the basic gates, if you guys remember, right? And or not gates. And we learn also about what? About how to move from one to the other. How to move from one gate to the other. Examples, it was like the NOR and NAND gates for changing to those. And also we underline this, we learn what is truth table, right? Truth table. And we use the truth table most likely, right? When we learn the truth table, we talked about the mean term and the max terms, right? Then we learn also the SOP and the POS, sum of product and product of sum. Then we extended the gates to have the XOR gate and XNOR gates. And we start building the equivalence using the NAND and NOR, right? Then we talked about what is critical critical path. With example with gates and how it's the longest one will be affecting in the shortest one and so on. Then we switch our gear to the chapter 3, I believe, which is basically the K-map. So what we have so far for K-map, we had 2 var, 3 var, and 4 var. People will come and tell me, oh, there is 5 var and 6 var. Yes, but it will be more difficult to remember which one is what. So that's why, up to 4 is enough. Okay. So that's basically what we have. And we have a bunch of examples about K-map and how can you play with K-map with X, which is don't care. Then we move into the combinational. Circuit. You guys agree? And in the combinational circuit, we learned the information about multiplexer and DMX and decoder. We looked about how can you build a decoder and gate level implementation, and then we start using little elements or combinational element to build a bigger elements, like multiplexer 2x1 can be used in a multiple networking layers to build multiplexer nx1, and same thing for the demultiplexers, and same thing for the decoder. Everybody agree with me that all of these things have been covered?
Yes.
Yeah.
Yep.
So
Yep.
yes. So what we learned before, it was build everything using gate level implementation, right? Do you guys agree? We need to see by our eyes why the gate level implementation limited, and why we don't implement with using combinational circuit elements. So for instance, there was a very nice example I give it to you for something is called full adder. Do you guys remember?
No.
We have done it when somebody was asking for the critical path. So the component of the full adder, if you remember carefully, there was like 3 different inputs coming into a block, and we are adding them together with carry out and carry in, right? So that was A, B, and CI, and then we have sum, and we have here something that's called C out. And even one of you came and say, oh, how did you write sum is equal to BA, XO with B, XO with CI, while carry out is basically A ended with B, ORed with A ended with CN, ORed with B with CN. Then I told you guys make it as an homework. Now maybe some of you remember this or not?
Yeah, I remember.
Yeah, thank you, I appreciate it. I really appreciate it. So I'm gonna start, instead of building with gates like this, to build with multiplexers, and even to build with what? Decoders. And that will be our subject for today. Using whatever we learn as a multiplexer, demultiplexers, and decoders to build combinational circuits, bigger circuits. Then we will move to the rest of the combinational circuits next week. For the exam, it should cover whatever we talked about even till today. And you're gonna see today the lecture is like a straightforward thing. Okay, how the exam gonna look like? It's gonna be straightforward, that you have a time slot from 8 a.m. to midnight. 8 a.m. to midnight.
How many problems are we to expect on the exam?
When I say 8 a.m. to midnight, it doesn't mean that the whole entire day you would be sitting and solving, right? The exam designed to finish the whole entire thing in 1 hour.
Okay.
Okay, I know that, you know, when you say 8 a.m. to midnight, oh my Lord, right? And we
Yeah,
will
yeah.
not and we will not have a lecture. So that means, you know, you can use the time of the lecture to finish, right? But imagine something wrong happening in internet, whatever. Then, you know, we have to go ahead and do what? You can use your time slot to midnight. Second thing, we're gonna use something is called grade scope. How many of you heard about it?
I've heard of it.
Yeah, I have heard of it, but I don't know how to use it.
No, you don't need to use anything. It's not a rocket science. It's basically the whole entire thing. Yeah, thank you for muting yourself. Anyway, so basically, how can you do it? It's very straightforward. When I will go ahead and bring the exam template in PDF, I will load it in grid scope. Okay. Then the grid scope will tell me from the roster which database for which course you're gonna add. So I will add all of your names. Then you guys will receive an email from the grid scope. That will be like, you know, that the same day or the day before. Then you will, you know, you will log in, you know, and you will be ready to submit. Then under the learning unit, there will be a folder called midterm 1. You open the folder of the midterm 1, you will find 3 files. What these files are? The exam in PDF format, exam in the document format, and then, you know, there is a tutorial about how can you use grid scope. Okay.
The exam is to be accessible via Gredscope, correct?
Yes. So, you know, when you finish, you're going to have it as a PDF and you will go ahead and load it there through the portal that you know, it will be sent to you, right? Automatically. Then, you know, when I will start grading, I will be grading in grid scope. Then I release the grades. So you will see in front of you every single elements and how much I give you. Then if there is a room, you have something is not clarified, why I got this grade here, then, you know, you can ask and I'm more than happy to help you. Is it clear? Be sure that, huh?
Will we be tuning into the Zoom?
What a second.
Will we be tuning into the Zoom for
No.
test? Okay.
I mean, you have just like do whatever you feel, you know. If you want, I can give you like a 5 minutes or 10 minutes Zoom on by the time of the lecture 1 o'clock, just to see whether that you have any problem.
Like questions, where do we have questions for the exam or anything? We can just tune in, ask you, and then just move on.
Yeah, I mean, okay, here's the thing. If there is a problem, I think it's better for me either that I will leave a PDF, a video, a recorded video. I will read the exam in front of you and I will load it into the learning unit under the folder called midterm, so you can watch what's going on. Or the second option, I will bring all of you in a Zoom at 1 p.m., I'm sorry, of the day, which is the time of our lecture, right? And then, you know, we're gonna go through the exam together. And if you have any questions, I can clarify to you, and that's it. So which way you guys prefer?
Option 1 seems cool.
Okay, I will just put a video.
Thank you.
A video like a 5 minutes. It's like nothing, you know. It's just like
That's fine. Thank you.
You're welcome. Okay. Grid scope is amazing for me and for you also. Grid scope will allow me to know who's cheating.
For grade scope, are we expected to make an account? Or is it, for grade scope, are we gonna have to make an account to log into?
You don't need to make. You will be. I will invite you.
Oh, okay.
Once I put your name there and say that you are one of the participants of the exam, automatically Gradescope will send you a link, because you will use this link to upload your answers, right? Huh?
Okay, sounds good.
No, the exam shouldn't be in multiple choice. Exam will be exam, you know. You will see. Have you seen the problems in the back of the book? Have you seen the problems in, you know, what we are doing in the practice in the in the lectures, you know, I didn't have any multiple choice, right? But if there is something like a multiple choice, I can bring you multiple choice. You know, there is no problem. But my multiple choice is not really straightforward. So it's up to you. Okay. Anyway, this is basically the whole entire thing. And then, you know, you guys will get used to within the midterm too, up to the finals. So everything will be straightforward. Another thing, we are computer engineer. Oh, you know, majority of us electrical computer engineers, right? So while you are solving your problems in this, I will, you know, I will put you the problem statement, then I will leave you spot to answer there, right? Be sure everything is written in a very clear way. Be sure when you load the PDF to the grid scope, I can see it. The system can recognize it. Because the system, if feel that, you know, you didn't put answers, you know, the resolution is not really great, it will consider you failing and it give an F. Because it's an automatic system, right? So watch out, you know, we should be able to use tablets, you know, stylus, you know, worst case worst, you know, you can have a scanner. There is actually something on the phone is called cam scanner. So you can be able to scan the documents on your desk and it will look exactly as a document. You know what I mean? We are ECE. So that means, you know, we should be aware of the technology. Sounds good to everybody before I start the lecture?
Yeah, sounds good.
Okay, now, because I see Leslie said that, you know, we didn't take the one bit full adders, so I'll just repeat it. So anyway, there is two different type of full adder, different type of adder, I'm sorry. There is one is called full adder, and there is one is called half adder. Full adder, half adder. What does it mean full adder? What does it mean half adder? It's a straightforward. This is also under the combinational circuit. Okay, so if you look to them, they are both of them are boxed. Box of what? Adder. What the inputs and outputs we have? For the full adder, I have the carry of the previous stage. And I call it CI, carry input. And I have the two operators that need to be performing adding on them, A and B. Okay. While in the half adder, I just have A and B. Sounds good? For the output, the full adder, it has the summation and it has the new carry out, which will go to the next stage. For the half adder, we just have sum and we have carry out. Have you noticed the difference between of them is to involving the carry input into the input processing? Do you guys agree?
Yeah.
That's called half adder and this called full adder. Let's look at the process for building them. So since this is an half adder, how many inputs I have?
Two.
A, B, and I have carry out and I have sum. Do you agree?
Yes.
There, I have three, right? I have A, B, C, N, and I have carry out and I have sum. This one is covering how many states? 4 states. 1, 2, 3, 4, right? While this one is carrying covering how many states? 8 states. So gonna be here 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. Sounds good. Mean terms, max term, mean terms are gonna be here, M0, M1, M2, M3, M4, M5, M6, M7. Here is M0, M1, M2, M3. Right? We're just applying adding here, right? So 0 plus 0, what are we expecting to be an output? 0, and there is no carry. Right? 0 plus 1, 1, there is no carry. 1 plus 0 is what? 1, there is no carry. 1 plus 1 is what? 0, and there is a carry out. Everybody agrees with me?
Yes.
Yes.
Okay. There, 0, 1, 1, 0, 1, 1, 0, 1, and 0, 1, and then 1, 1, and the rest are zeros. Everybody agrees with me?
Yes.
So in that case, if I go into the git level implementation, it is very straightforward, right? In the git level implementation, I don't even need Kmap. Do I need Kmap for this table? I don't think so, right? Because sum pretty much is acting as what? XOR, right? This is the truth table for XOR for sum, right? So basically I can say sum is A XORed with B, while carry out is basically this element, which is the mean term 3, which is basically A ended with B. All right? So I wrote the equation describing this. Here I need Kmap. Do you guys agree?
Yep.
So how many Kmaps I should come and get out of this? 2. So this is 3 var Kmap. 1 it will be for the sum, 1 it will be for the carry out. So 1, 2, 3, and here then have A, B, C, and 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. 0, 1, 3, 2, 4, 5, 7, 6, right? Okay, let's put the numbers. So M0 is 0, M1 and 2 are exist, 1 and 2 and exist. And then, 4 is happening, and then, 7 is happening, and the rest are 0. This is what? Checkboard. Do you guys agree?
Yes.
Which is mean that, sum in this case will be A XORed with B XORed with the CN. Sounds good? Now we need another Kmap, which is basically for the carry out, right? So like this. A, B, C, N, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. And they're going to be also location 3. Location 5 and 6 and 7, right? 5 and 6 and 7. And the rest 3 will be zeros. So in that case, how many groups I have? 3, right? 1, 2, and 3, right? So the carry out is going to be what? This group will be A with CN. This group will be A with B. This group will be B, CN. What do you guys think?
I have a
Hello?
quick question.
You can have 2 questions.
Where'd you get the ones from again? From the you got from the board, but I forgot to forgot where you got them from. Oh, from right there. Okay.
Have you noticed this? This arrow going down like this? That's like a step going to 1 to 1 to 1 until we get out, right?
Okay.
Sir,
Git level, yes.
can you go up a little bit for a second?
Yeah,
Thank
sure.
you. Perfect. That's good.
Okay. Now, implementation git level, I can ask anything. Make it and make it NaN, build everything with NOR, and you will do it, right? With respect of the critical path and all these things. Straightforward, right? Okay, that's really cool. What about if I would like to build a full adder from half adders? How can I do this? By the way, when I say full adder, half adder, this is just an example. I can make you a new example in the exam. It's just a circuit, right? I'm describing something happening and you will just follow the same footsteps, right? So let's imagine that I have half adder in my pocket and I would like to build a full adder. What should I do from your point of view? So if you look very carefully to this table and this table, you will find out that two half adders can build one full adder.
They're just flipped.
This guy can be used to build this guy.
Yeah, you just need one of them to be a knot, right?
I mean, let's see, I don't know, we'll try. There is also another thing. If I have full adder and I want it to be half adder, I can put C with equal 0, then I'm talking about a specific location, right? Or I can make A equal 0. Look, if the A is equal 0, so then you know this table exactly like this table, right? Do you agree?
Yeah, that makes sense.
So you can imagine infinity of tricks I can build, you know, because I love tricks. And I think all of you like tricks. Do you guys agree?
Mm-hmm.
Any question? So let's build the full adder from half adders. So this is basically what is available for me, and those are the one I need to build, right? So how can I do it? It's not really hard. So think about it as follows, right? I can come here and say I have a full adder, sorry, half adder, and this is an A and my B. Then I have a carry out, I have a sum, and I have a carry out, right? And this is my first half adder. Then I have another half adder in my hand. Everybody agrees with me? So this half adder, it can go here. No, sorry. This is carry out and this is a sum. So I can take this here and I can take here to be carry in. And then, you know, they're gonna be the AB of it. And here is a half adder. And then the output will here official sum. And the carry out here, this is the carry, this is a sum. The carry out here will be what taking these two guys together into an OR gate. And that will be my official carry out. So did you see what I did in front of you? Using two half adder, I built one full adder. That makes sense? Testing it is really straightforward, right? Because, you know, sum is the XOR, right? Everybody agree with me? So I'm XORing A to B. And then, you know, I'm taking this and XORing it to CN. Then, you know, this is the sum. That makes sense? Hello?
Yeah.
Is it straightforward to everybody?
Yes.
Okay. Now we're gonna move into what about if I just have in my pocket decoder and I would like to build half adder, right? So I have in my hand decoder and I want this decoder to perform with some gates half adder, right? So in this case, that's not really hard. Do you agree? Because if I have a decoder 2, 4, so that means there is 2 input and 4 output coming out 0, 1, 2, 3 like this, right? I can make it look like a half adder. How? So if I look to my table here, A and B are the inputs. Everybody agree with me?
Yes.
So in that case, I can put here A and B. Then every single output will be in this table discussing about what a specific element. What is M? This is 0 can be acting as M0 and 1 acting as M1. So you can make it like this: M0, M1, M2, M3. Every single one, it's actually M0 and 1 and 2 and 3 from whatever we learn about decoder. Do you guys agree?
Yes.
For the rest of you guys, everybody straightforward, understand what I'm saying?
So would that be the sum or would that be the carry out?
We haven't even sum or carry now. We just say that
Oh, okay, got
M0 to M3, right?
Okay, got it.
Makes sense? And when I sum and carry out, here's the thing. Look, change the color, and then I say here, oh, good. For the carry out, M3 is the only one carry out, right? So I can just extend this one and say this is my carry out. Then in the sum, M1 and M2 are the exist for making this function 1, right? So I can say that M1 with M2 ORed, that will be my sum. By adding this gate, which is an OR in front of you, I provided you the sum coming out of decoder. Just with OR gate, I'm done with the decoder to bring you half adder. And the output here is the sum and carry out. That makes sense?
If you wanted that circuit to be an XS3, would you use M0 as your final connection? And you would just
Yeah, I mean, that's a different problem to design. Yes.
Right. Okay.
Okay. What about if you would like to build full adder? Full adder, it has 3 inputs. Do you guys agree?
Yes.
So in that case, I need 3, 8 decoder. Make sense?
Yes.
So if Professor Ali give you 2, 4 decoder, then what you're gonna do? You have to put the 2, 4 together to bring it 3, 8, and then you will just connect, right? Does make sense?
Can you say that again?
If I'm telling you build to me full adder using bunch of 2, 4 decoders, what are you gonna do?
We'll get
Disconnect it.
Exactly.
yeah.
So first of all, you're gonna bring some of the 2 4s, you connect them together to make it 3, 8. Then you will use the 3, 8 for the process, right?
Yes.
That's
Can we do
exactly
that?
what I was saying.
Can we get the 2, 4 decoder for this problem?
Yeah, but I meant it before, right? So, okay, here, here is the 2, 4, right? You forgot about it? So here, here is the 2 inputs. And
Oh
this
yeah,
one is the same thing.
we have to add
And then, you would have here the enable. And then, that will be enabled, that will be connected like this, right? This is
Yeah.
2, 4. This is 2, 4. And then, here 1, 2, 3, 4, 0, 1, 2, 3. Here 4, 5, 6, 7. Do you agree? And then here is the 3 inputs. In this case, it's gonna be A and B and C N, right? Here's the 3, 8. Then you will start looking into the candidates for the sum. For instance, the sum M1 and M2 and M4 and M7 are there. M1, 2, 4, 7. M1, M1, and M2 and 4 are 7 or together they're gonna bring me the sum, right?
Yes.
Then I can also be tricky until you build it with NAND gates. So instead of this OR gate, you gotta make it NAND gates, right? That makes sense?
Isn't that De Morgan's?
What do you mean by De Morgan's?
Changing from or to and.
I mean, you will see how can you change the OR gate, right?
Yeah.
Yeah, and then you can make it multi-ways. And if I say 2 input OR gates, so here I just make it multi-inputs, but I have 4 inputs. So in that case, I need like an OR like this, taking 2 of them, or like that, taking all of them, and then another OR like this, and then gonna be those 4, which is gonna be 1, 2, 4, 7, and here gonna be the sum. Because at the end of the day, you want this critical path to be exactly, the passes are almost the same, right? Make sense? Hello.
Yes.
Okay.
Is that
No.
a 4-input OR gate? Just asking, or is it a?
This one?
Yeah.
It is OR gate, right? Or this guy.
There's
this
multiple.
This is OR.
Oh, there's multiple of them. Okay.
This,
Yeah, you can.
yeah, I mean, like a multiple input OR gate. You can do it still. Okay. Anyway, what about if I like to build this full adder using multiplexers? Very easy, right? Let's make the table again. So we have here A, B, C, N, sum, carry out. 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 0, 1, 0, 1, 0, 1. 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. M1, M2, M3, M4, M5, M6, M7. Right? So gonna be 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1. If I want to build it with multiplexers, there is a way to do it, right? First of all, a problem like this in front of me, how many outputs I have?
2.
So how many multiplexers I need? 2 set
Two.
of multiplexers, exactly. Second, if I have a 8 states table, I can make it actually with 4x1 multiplexer. Okay, let's try. So I'm gonna build a multiplexer for the sum. So I have a 4x, right? 0, 1, 2, 3. You guys agree? And this, how many bits for this multiplexer selector will be?
1.
Why 1? If it's 1, why? If it's more than 1, why?
Oh, it's
let's
log
just-
2. Log 2 by 4, right? So it's.
It should
Oh,
be
it's
2.
2.
It
It's
should
2.
be 2. Should be 1 or should be 2?
2.
2. I can't do logs.
It's a log 2 4. It's 2. So here is log 2 of 4 is equal 2 bit. Make sense? Here is gonna be the output sum. Let's see what we're gonna do in the input. I didn't put anything on the input wires, right? So the selector will be AB. So I'm gonna make it here AB combined together is my selector. So let's make a small table like this. AB 1, 2, 3, 4. 0, 1, 0, 1, 0, 0, 1, 1, right? And I need to see this wire when it's 0. When I will see 1, 2, and 3. Let's see. 0, 0, right? So I have 0, 0 here, and I have 0, 0 here, right? Do you guys agree?
Mm-hmm.
Okay. Carry the sum is equal 0. Huh? When is 0, 0. Do you guys agree? And the Cn equals 0. Right?
Mhm.
And when it's 0, 0, also the sum is equal 1 and 1. Right?
Mhm.
So pretty much I can make this while what Cn. So when I pick up 0, 0, that will be the case. Right? Then it depends on my Cn, the sum will be happening. If the Cn is equal 0, the output will be 0. If the Cn is equal 1, the output will be 1. So far, so good.
Yeah.
Let's now move to the next possible thing, which is 0, 1. In a 0, 1, this is basically our case. Right? So if the Cn is 0, sum is 1. If the Cn is 1, sum is 0. So this is actually what inversion relation. So I pretty much I need to be Cn complement, or you can make NOT gate connected to Cn. Then when the 0, 1 happen here, when Cn is equal 0, the output will be 1. When the Cn is equal 1, the output will be 0. Make sense?
Yeah.
Now we're gonna move into the next candidates, which is 1, 0. And 1, 0, same thing as the one before, right? So it's also Cn. And in that case, if you can see, if the 1, 0 happened, this will be the output. Then the last thing is gonna be this 6 and 7 here. So 0, 0 is 1, 1. So basically gonna be what? Cn. So pretty much by using AB as a controller, using the Cn as an input of the multiplexer, the output coming of this multiplexer will be performing summation. So this setup in front of you is the summing of the 1-bit full adder. So did you see what I did?
So can we reduce it to 2x1 multiplexer?
You can do whatever you want. It's not very hard. It's just, it's you know, you can add more gates, right? Because the rest will be something going in input, right? Have you
Yeah,
noticed when I made it like when I make it 4, 1, because I like just use wire here, right? Wire, invert. But you know, if you're gonna make it 2, 1, then you know the other 2 variables, you have to go into the wires, right? You understand what I'm saying? So instead, if 1, it's gonna be 2 of them going inside, right?
Yeah, that's right.
So you're gonna add more gates.
Mm,
Compromise here, right?
okay, got it.
Yes, let's do the sum. So the sum 1, 2, 3, 4.
Professor?
Do you mean to see
Yes.
out?
Huh?
Almost see out.
C out, exactly. So let's make a C out and gonna be also AB. A and B. Those are the 2 inputs, right? So now we're gonna do the same thing, right? This is the 0. And when Cn is 0, output is 0. When is 1, output is 0. So that means, you know, this wire, it will be connected to the ground. It doesn't have any relation with Cn. So just connect this to what? 0. Then, you know, you're going to go in the second one. If it's 0, it's going to be 0. If it's 1, it's going to be 1. So it's going to be Cn. Then you're going to go in the third one here. Going to be, if it's 0, it's going to be 0. If it's 1, it's going to be 1. It's going to be Cn. Then the last one, you know, if it's 0, it's going to be 1. If it's 1, it's going to be 1. So no matter, it's going to be 1. So this is 1. And now with using these 2 multiplexers, I perform the full circuit of 1-bit full adders, as you can see. Pretty much, we just have like a 1 NOT gate, right? Because, you know, you can just invert 1 time Cn and that's it, right? Make sense? and 0 is connected to the ground, and 1 is connected to the VCC. Sounds good?
Mhm.
Yeah.
So we learn how to build using decoder and what multiplexers in a higher level of abstractions. So we decrease less number of elements added to the graph. So that's why it's showing you how it's very important to have more combinational circuit, helping me to decrease the routing and all of this complexity on how the graph look like, right? There is infinity things I can ask you to do. So imagine that I'm asking you for a circuit. It has 3 inputs, and the output is actually majority of 1 per state. So that's called majority encoder. It's a type of encoding. Again, so here is a box, and this box is performing something that's called match with majority, right? It has 3 inputs, and the output is depends on how many ones I have. So imagine that I have here A, B, C, and the output is called it OP. And in the specification, if majority of inputs are 1, then OB will be 1. Let's translate this in what? Truth table. So you're gonna go ahead and you build your truth table. How many inputs going into this box? How many outputs coming out of this box? Hello? Hello?
3 inputs.
How many inputs going in this box?
3.
3. A, B, C. How many outputs I have?
1.
Exactly. How many states this table is covering?
8.
Let's do it. 1, 2, 3, 4, 5, 6, 7, 8.
Does this thing does not have a selector?
Huh? No, it doesn't have any selector. This
Okay, got
is majority. It just came into it. Okay.
Okay.
Okay. 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. Right? What was the specification describing the transfer function between input and output? The majority will be 1, right? So all of them have zeros. It's 0, right? Here, there is 1 in front of 2 zeros. Who is winning? 1 or zeros?
0.
Exactly. Here, the same thing. 2 zeros in front of 1. 0 is winning. 2 ones in front of zeros. 1, 0, 1. 1, 0.
Sir, I think it should be a 0, right? 0, 1, 1, 1.
Right?
The second, third last one should be 1, 2. Right?
It is 1 here.
Yes, the third.
We have the 0. The last
The one
0.
above it,
Yeah.
Correct.
and then the one above it should be a 0. Yeah. Okay.
Correct. So you agree? Everybody agree with me?
Yes.
Yeah. This thing remind you is what?
OP's output.
No, OP remind you is something we just talked about it like a few seconds ago.
Well, that one's like an AND gate, and then the other one is an OR gate.
I will draw the K map and then I will tell you. If I would like to make a K map for this, look. That's A, B, C, right? 0, 1,
It's
0,
the checker
0, 0,
situation,
1.
right?
Huh?
The checkerboard situation or the
No,
chess.
no. Oh, sure. Just
Mhm.
wait. M0, M1, M2, M3, M4.
It's like a keyboard thing. The keyboard up, down, left, right.
Oh, that's actually the K out, the C out of the full adder. Right? Think about it, right? 0, 1, 3, 2, 4, 5, 7, 6, right? So 5, 6, and 7 there, 5, 6, and 7 there, right? And this is 3 here. Do you remember this? That was this guy. Right?
Yeah.
So this is actually a circuit of what? 3 input majority encoder. So one of my exams, I came to them and say, build 1-bit full adder using XOR gate and 3-bit input majority encoder. Nobody solved it. Can you imagine?
You said what, Professor?
Build 1-bit full adder using XOR gates, or even I say with NAND gates and majority encoder.
And what would the majority encode imply?
This guy. Right? So you can just pretty much say that, here is my XOR A, B, C, sum, and then, I take those 3 guys and put them in majority encoder, and I get the carry out, right? That makes sense?
That makes sense.
That was 20 points out of 100.
They had to do with NAND, right? So they had to put they had to build the XOR gate with
Yeah,
NAND
you're gonna
gates.
make you this NAND, yes. Some of my questions, it's even more tricky. Which is basically like, if you look to this table, right, you can make anything you can imagine, right? You can break it. You can build it with pieces, right? You can put multiplexer, demultiplexer in the middle of things. You can make it like a spaghetti sauce, spaghetti, somehow middle of things, and then you can build something. It's like, while you guys are, somebody said, can you explain that OP part again? Sure. Can I ask you a question, Alejandro? Look at this. Did you see this? Remember how it looked like? There is one in M3, and there is, M5 in this location, M61 and M7, right? Look at this table, right? M3 is 1, and those are 1s exactly. So, and this is the carry out. This carry out is that. Okay. Anyway, so basically, it is like Lego. You guys, who actually you like to play with Lego? You guys Lego, or you don't like Lego? Digital logic design is basically pieces, and you try to match the input and output, and then you will just build something, right? It doesn't matter, how it looked like. You just need to figure out how can you rotate it, maybe. Then it will go ahead and match and attach to the second part, and so on. Sounds good. What about if I like to build this circuit using demultiplexer? How can I do this? Somebody can give me an idea of how can I do it? Huh? Hello.
Sorry, what was the question?
No, I have a demultiplexer this time. How can I build this majority encoder using demultiplexer? How? Any idea how can I do it?
Would it be B and C?
We can try. So one of the possible way is actually to make it here 1. It's connected to the VCC, all right? And I make this what 0 to 7. So it's gonna be what 1 8. So they're gonna be 3-bit. Do you agree? And those 3-bit will be what? A, B, C. Right?
Okay.
Then when is ABC equals 0, my output is 0. Do you guys agree?
Yes.
So in that case, I take this one, it will be 1, so I invert it. All right. Then it's gonna be like this 1, 2, 3 zeros. So gonna be here like this. Right? Then number 3 gonna be 1. So number 3 gonna be just a Y. Then number 4 is gonna be 0. So gonna be here. Then number 5, 6, 7 is gonna be 1s, right? Then I will take them and what OR them. Boom. So I build this circuit now using demultiplexer. Do you guys agree?
Can you make the input A and then just use B and C?
You can try. So what? Try. Right? This is more simple, right? Because don't forget A is a variable, right? Do you agree?
Yes.
Then you're gonna make it more difficult. So you can actually make it maybe you can make it 2D max, and then you will take the output and you order them together. So when the A will be 0, something will happen. When A will be 1, something else will happen, and you combine them, right?
Mm-hmm.
It's double, right?
That's right.
Yeah.
If we only have like 2-bit for the enable, wouldn't we need to have 2 multiplexers?
What do you mean by enable? You mean selector?
Yes, a selector.
Okay.
If we had only 2, that means we will need to have the number of output only gonna be 4, right?
Yes, you can, either you can build it with bigger or you can take care of it, right? Hello?
You say I can do what?
Did you hear what I said? I made it here in front of you for the 1-bit full adder with 2-4, right? With
Yes.
4-1, right? Here I make it in front of you with 4-1-8, right? So you can make it up to 1-8 in this case because it's three inputs, right? You can make it also 2-4, right? Sorry, 4-1 multiplexers. You understand what I'm saying? Here, look. In this example, right? The full adder, right? Did I use 8x1 or did I use 4x1?
4x1.
Exactly. Can I do it with 8x1?
Yes.
Same thing there, right?
Mm.
Okay, look.
Yes.
Any questions? Any problems?
Just nervous about the exam.
Exam is fun, don't worry.
Okay.
It's the most fun part of the course,
That's it.
Yes.
Can we go back on the diagram? So why are you adding negative? Can you just explain it back? Like why you adding NOT gates in front of some of the outputs?
You mean here?
Yes.
Okay, can I ask you a question?
Yes.
If the ABC is 0, 0, 0, right? What will happen?
Output's gonna be 0.
That mean this one will go here, right?
Oh yes.
Okay, so that means they're gonna be 1, right? But then I don't want it 1. I want it to be what?
0.
Exactly.
Oh yeah.
Right. Sounds good.
Yes.
So you can do this with like any bits. You can do it with C bit, right? Or BC or
Exactly.
anything that you want. Okay.
Exactly. Okay. Any other questions?
Just the last
No.
part. So why did you put an OR gate at the end of that? Because all the other one will be set to nothing, right?
Yes.
Oh,
Yes,
but
no.
you want it as
I-
just a one.
No,
Or sorry,
I
one
have a
output.
question for you. OP is equal what?
Oh yeah, one output. Yeah, one.
Right?
Got it. Mhm. Got it. Makes sense.
Super.
Yeah.
How many questions is on the exam? Infinity.
Huh?
Somebody else. Yeah, infinity. Yeah.
At least 40.
Yeah. but-
Between 80 and 85. You know,
Okay.
I haven't. You know, I
Oh.
haven't set my mind. You know.
Okay.
Times by 2. Understand it.
So, Professor,
Yes.
that means your exam is not set in a way that it's supposed to be done in 1 hour 15 minutes.
Yeah, you know, it's gonna be infinity questions finished in 1 hour 15 minutes.
Is it even possible?
I'm a magician. You know, I can do it. You know, it's not really hard. Okay. The whole entire idea that you already have a plenty of time, right? You have 8 a.m. to midnight. The exam is made in a consideration that people also work. They have the other stuff to do, right? So
Can we do it on-
don't worry about the difficulty levels. Just
Can
worry
we-
about how can you be tricky. Yes.
Can we start it on Friday? Wednesday's my busiest day of the week.
I know, but you know, you can do it on the time of the
Okay, all right.
midterm. I mean, with the lecture, right?
Okay.
Because you know I have to follow my regulations, right?
No problem. No problem. I understand.
Okay. I appreciate it.
Thanks.
So-
Professor, the exam is not on auto submit, right? We need to submit.
How can you make it auto submit? You know, it has to be submitted by you. So you know,
Oh,
you have to
okay.
take a PDF and you go submit it to the grid school.
Oh, okay. Because great Blackboard sometimes has like auto submit too.
There is
so-
no Blackboard on this.
Okay.
The only Blackboard on this, you find a folder has the PDF format of the exam and a Word document of the exam and instructions in a video format and also instructions in the PDF about how can you use a thing.
Sounds good.
Yeah.
Professor, what if I just become the multiplexer?
Huh?
Yeah, just become the circuit itself. I'll
You
just do the crunching for it.
You can build a multiplexer,
No. I become the multiplexer.
You want to be a multiplexer?
Yeah.
Good. That's very good.
Preferably a 1x8.
Okay. Then, you know, I will make the exam more than 8. Then, you know, instead, you know, you have to build a bigger multiplexer. Okay. Okay, guys. So have fun. And, you know, it was my pleasure to talk to you today. Hopefully you guys are enjoying the course and, you know, the material. And honestly, the material is very straightforward. Let me make it very clear. This is the gate for computer engineering. Okay, so if you understand this course, you will be able to understand logic design for the microcontroller. You will be able to understand the digital logic design like HDL languages like Verilog, VHDL, and System Verilog, which is a courses we have here in, for undergrad, which is like for 3300 and 4304 and 4305. And then also 4300. If you understand this, you will understand computer architecture. Because I can build with these pieces later on in front of you processors. Okay. And there is a wide range of jobs in the market just for this digital logic design. You know, let's call it digital engineer. Of course, there is some people work in the analog, which is kind of a little bit different than us because, you know, we work in this continuation and then, you know, they work in continuous mode. Okay. Any questions? If there is no question, it was my pleasure to talk to you guys. Please stay safe and God bless you. And I hope that you guys will have a good time with the exam on Wednesday.
Thank
Have a
you.
good,
Thank you,
Have a good
guys.
one,
God
Professor.
bless you. Have a
Thank
good
you,
one.
Professor.
Thank you. Bye-bye.
Thank you, Professor. Have a good
Thank
day.
you. God bless. Thank you. Bye.